That's interesting. I did not expect that. If you connect the VGA while you're asleep, Linux doesn't like it. The detection on waking is bad. But
Is this garbage or not? What do you think?
You can just leave it.
Shouldn't we recycle and
Person might come back. Should recycle somebody's notes before they
what is our VGA?
Oh, that is how I love you.
That is very strange.
Is your screen gone? There you go.
Yeah. What do I have? Hey now. That tells me I do have 1024 by 768.
So this is also part of the lecture.
Yeah.
It's called.
Well, we can start off by asking if there are questions about the project at the very least.
Is it due on Thursday?
The project isn't due on
No,
Thursday.
That's,
Can you get it done?
No, I mean the abstract.
The proposals.
Proposal.
I think proposals, it'd be good to have proposals in by Thursday, so that way I can look at them and say, we need to sanity check this a little bit or something like that, so I can give some feedback. And that way people can actually work on a project over the next month. Because otherwise, you might be working on some project for your term project, and it might not be a viable term project, which would be unfortunate.
Can we have a template for that? Like what you should
Sure, yes, I can do that. I should write this down.
you mean template for the proposal?
Yeah.
There.
Okay.
So this is all very, very fun. Let's see. Let's see if I can set aside that way. Now things are compatible. 1, 2, 3, 4, 5, 6, 7. Okay, so we're still missing 1, and I know 1's going to be absent. Okay. Let's see. Okay, there's one of them. Okay. I guess we'll just go with this screen, and I'll look at the screen a lot, and that's okay because I'll probably do that anyway. Does make navigating a little bit funnier. So I'm going to be working from Abik's slides this time. But this paper is SemFix, right? So we've talked a bit about debugging so far. And in particular, we've talked about, not these things, but we've talked about things like fault localization, right? We've talked about slicing. And fault localization gives you some notion of an estimate as to where a fault might be. Slicing gives you some better notions as to explanations of bugs. And in contrast, notions of automated repair, and there are several different types of automated repair, try to automatically create fixes or automatically generate patches for buggy programs, which is kind of cool. I mean, there's this idea that you're coming up with a fix for something so that the developer doesn't even have to do that part. And prior to this SemFix work, most of the existing approaches used genetic programming techniques. Who is familiar with genetic programming? Anybody? Okay, a little bit?
Yeah.
Can you give me a...
Like genetics, taking multiple different types of pieces of the program, recombining them together, and then seeing which ones survive, and then transforming those.
Sure.
Genetic search of in program space.
I'll go with that. I'll go with that. So we've got this familiar notion from genetics where we have, we've got genes which code for different behaviors or something along those lines, and then as these genes, as you look at the evolution of a genome over time, you can look at how certain fitness factors affect, well, if we have a duplication of a gene over time, if that makes this better in terms of the evolutionary benefits, then this duplication will be maintained over time. So you look at these perturbations of properties, and this means that you can say copy information from one place to another, or delete information in one place, or mutate information in one place. And this will affect the genome. This is just doing those same sorts of things to code. And so existing approaches for generating these patches would do things like copy code from one place to another inside a program to see if it can fix it, or remove some code, or change code under some very constrained ways. And if you do this a whole lot over many trials, and you allow those changes, which seem to have an advantageous benefit to the correctness of the program, to survive, then you have this net effect of identifying things that are beneficial that create a patch for the underlying problem. Reasonable enough idea? So that's where, that's essentially the prior work to this. And one of the problems with that is that if your solution doesn't fit inside that genetic search space, then you're not going to find a solution. So what do I mean by that? Well, if you can't find a solution by duplicating code, by copying code from one place in the program to another, or by deleting some portion of code, or by using some strict set of small changes, local changes to code, if you can't find a fix by doing those operations, you're not going to find a fix. So that's the limitation of this search strategy. And so the goal of this work is to move beyond that limitation and work instead from the semantics, or as they're putting it, using symbolic execution to extract what the correct behavior ought to be. Use that to identify what the fix ought to be, instead of these scale genetic-based approaches. Okay, so the underlying flow of things is that they're going to start off by using statistical fault localization, which we're all familiar with by this point, right? Can someone give me one example of statistical fault localization?
Tarantula.
Tarantula, yes.
Start from O.
OCI, yes.
OCI
There we go. Yeah, and those are the most common ones at this point, and there's been some work out that even shows that in general, variations of OCI, variations of Tarantula perform better than the other statistical fault localization approaches, usually. Okay, so we're going to start off using that. And this gives us some intuition as to what places inside this code are likely to be buggy. And if we're looking at the context of repair then, what does that tell us?
So they're using the default Tarantula, not the test purified version.
Yep. And you could combine all these things. That's absolutely true. I think that's probably where you're going, right? It's semi-orthogonal to the core of their problem, so they don't discuss that, which is not too uncommon in research, although they might be able to gain some speed benefits or something like that in doing so. But suppose that I get this, what does statistical fault localization give me, again?
Ranking?
A ranking. Right, it gives me a suspicion ranking. So it tells me a list of the statements in order that I believe they're buggy. How is this relevant to repair?
Get the most suspicion, try to fix it.
Yeah, absolutely. It's essentially a priority ranking for the places I ought to be creating some sort of repair. Seems reasonable enough, right? Okay, so they're going to work with that. They establish their suspicions, and then they feed that into their symbolic execution. And they're going to use symbolic execution in such a way that it tells them how these buggy locations ought to have behaved. Which is kind of interesting. We'll see how. That's kind of counterintuitive. I see some brow furrowing. You might ask yourself, how can you figure out how it ought to have behaved? There are some limitations, there are some constraints, and we'll see those.
Is the kid telling us what you ought to have behaved, or the constraints of what the bug has, like the area of values that it would have to fall in, the bug would.
It tells us to a certain degree what would be necessary at this program location in order for the program to behave correctly.
Okay.
That could be done like if you have a test suite and you know exactly what the output should be.
There you go.
And then you can do it.
Yep. And we'll see exactly that. With a little bit more glue and there are some nits that come into play as you start to approach that. But your intuition is good. That's essentially their approach. The test suite gives you a notion of correct behavior, so work with that. Okay, and so once you've got that, you've got this notion of how things should behave. The question is, how can you use that to derive a fix? You've got constraints on what the outcome should be. How can you use that to derive new code? And so we're going to use a technique called program synthesis in order to do that. And I think the only thing that's new to us here is program synthesis. In terms of the high-level techniques, there are some new things in here as well in terms of how they use it, and we'll go through that. But in terms of the big concepts, the new thing here is the program synthesis. That's kind of interesting, the idea that you can create a program that satisfies certain constraints.
So they use the code from the program itself that already works.
They generate new code. Yeah, indeed. That's the idea of program synthesis.
Am I correct that this program synthesis, they can synthesize fairly simple statements?
Yes, this is true. That
So the fixes that their approaches can resolve are not very elaborate.
This is true. This is true. Most bugs are not all that elaborate either.
Yeah.
So that's fair. If we're looking at this isn't always going to work, and we accept that going in, then yes, that's the idea. We'll come back to that. I mean, there is more subtlety to that, so it's good to keep that sort of thing in mind. But yes, yeah. So they're looking at synthesizing simple code snippets that will satisfy these correctness criteria. Okay, so that's the big picture. So if we now dive into this just with an example and go back through these steps, we can have a notion of a snippet of code here. And so we've got just a very short function from a very common debugging benchmark known as the Siemens debugging benchmark suite. And this is from a program called TCAS, which is just a traffic collision avoidance system. It's a very simple function, but there's a bug right here. It has an injected bug where bias is set to downset, and it should be set to upset plus 100. Okay? So that's the incorrect line. And they have a test suite. And this test suite tells us that with certain inputs, the program still works, and with other inputs, the program is buggy. So what do we do with this? Based on...
We synthesize new program that will solve the issue.
Okay, that's giant step, baby step now, baby step. That's...
No, the first one, the suspicion statement duration?
Yeah. So we're going to actually do our fault localization and establish some notion of suspiciousness. So we start off by essentially running Tarantula. Yay. And this gives us our ranking here, which tells us conveniently that line 4 is very suspicious. How fortuitous, right? Because we know that's the buggy line. Okay. So Tarantula tells us where we want to look. Now suppose that it didn't, that this wasn't the buggy statement. This is still the first place we would try to create a repair. And if we failed to do so, we'd go on to the next place and try to create a different repair.
It could, if the first suspicion line, if you modified it in such a way, there is a good chance that you can modify it to fix the bug by introducing yet another bug.
This is especially true for this particular benchmark. But yes, in general, you hope that's not true. And for sufficiently complex software, it's less likely to be true. There is, however, a surprising amount of intrinsic redundancy inside software. So you have this chance of creating something that is coincidentally correct. Looks like it's correct. This is a real problem.
Well, authors defend themselves. They say that it's easier to verify whether the code fix will indeed work or not. So
Yeah.
it's like, imagine this program will generate some patch,
Mhm.
and then it will undergo code review.
It's easier to accept the bug than write the bug. I mean, wait, accept the bug fix.
It's pretty easy to accept the bug as well.
Yeah.
But yeah.
Yeah, you tell it's a feature.
But your intuition is right. That there's this notion that if you have a fix, it ought to be easier to validate that fix than to necessarily come up with it right away or recognize where it needs to be, what it ought to be, and so on. This is true. Okay, so we're going to dive into this statement and try to generate a repair for it. How are we going to do that? We're going to use symbolic execution. So we're going to look, in this case, we'll start off just by looking at one of these failing tests. Now we'll see that you don't just want to use one test later on, but just to drive the example, we'll take one of these failing tests and try to see how that tells us what the behavior ought to have been, right? So if we use symbolic execution, traditionally symbolic execution, like the way we saw it earlier, we don't have a notion of test inputs that are concrete, right? We start off, like we saw with Dart, these test inputs would be symbolic and we'd be generating a large number of tests. And that doesn't give us an intuition as to how this program ought to behave given a particular input, does it? Because those inputs are symbolic. So we have to do something a little bit different. Instead, we say that the result at this statement is symbolic. So the inputs are concrete. We still have concrete values for inhibit, upset, and downset. But the result at this statement is treated as symbolic. And so now what this tells us is that we're going to derive constraints using symbolic execution over the result at this statement, at our repair candidate. And so we can explore different paths through the program. And we can see that if we go down the true branch here and encounter 1, then that's the expected output. So that is something that we want to be true, and we'll say that our constraint along this path is that the constraint over this statement's result, right? Because we're taking this bias equals something and making it symbolic. The constraint over that result of the statement is that x has to be greater than 10, because that's the path condition here, right? So to reach this correct outcome, this path condition would have to be true. So that is one of the possible ways that we can get the correct result. So that is one of our potential constraints over the behavior. Does that seem clear? Okay. Alternatively, if we take the other branch, then we get 0. So this path does not provide a correctness constraint. So we only have that x must be greater than 110 for this test. And we don't have any correctness constraint over here because this was incorrect. Clear? Now that's used for one test. That tells us what would have to be true here, given these inputs, in order for this test to behave correctly. Right? And we can use that information across all of the tests and the test inputs tied to the constraints for all of the tests to determine a global constraint over the correct behavior at that statement. I see a question.
Depends so much on the test input.
Different.
It depends so much on the test input. For example,
Mhm.
at 100, if I take all the test cases which are say 80, 90, and 120 and 1020, then I may not reach at 100.
Okay. So if you cannot synthesize a repair for a test input, what you're essentially saying is there was no path from using that concrete input, there's no path from this statement that can lead to correct output. In which case, if that happens, you have to move to the next candidate because you can't create a repair here. So this isn't the place you want to patch. So look somewhere else where you can create a patch. Is that fair? I see another question kind of for me. No? Okay.
How far down the path, because you're following, line 4 to line 7, so you're following down the path, the program.
Mhm.
And you're continuing the symbolic execution beyond the bug. How far do you go?
You essentially need to go to the places where correctness is measured. So output points, and probably even the exit.
That could be a long ways away.
That could.
I guess the more specifications on the variable makes it easier.
Maybe. So the comment was more specifications over the variable makes it easier. Let's keep that in mind, especially when we start to look at the results.
Okay.
Okay?
Keep that in mind.
So yeah, keep that in mind. Okay, but you can see how we can get a constraint that reflects the correct behavior for just this input by looking at, oh, we got the correct output here, so we can add this constraint. All reasonable. Okay. So this is kind of what this gives us. We have this notion that we have an abstract function here over the concrete state of the program at that point. And the question is, what is this function? What is this function f? Right? And we're deriving constraints over the behavior of f. Given these inputs, f should have this, this constraint has to be true in order to get a correct result. Okay? So we have these constraints over f, and we don't know what f is. This is kind of interesting. So far, when we've looked at constraints, we've talked about first order logic, right? Which is this notion that we have these terms, and we're looking for some assignment of truth values to the underlying terms so that we can see if something is satisfiable or not. Let's frame it as satisfiability, right? The question of second order logic gives you notions of, does a function exist such that? So we'd no longer be necessarily solving for a particular assignment of truth values to terms in satisfiability. We're searching for a function and trying to solve for a function. And that's this notion of second order logic, which is kind of cool. Although there's controversy as to whether or not second order logic has any utility, it's at the very least a good way of expressing the problem. There's debate within the logic community about that. Okay, it's at very least a convenient abstraction, and we're all about abstractions, right? Okay. So given this, we have these sets of accumulated constraints over all of our tests, right? At this particular program point, with this input, what had to be true in order to get the correct output? We can drive those for all of our tests. And so we just need to find some function that satisfies those constraints. So this is the idea of solving a constraint over second order logic. What is f? What must f be in order to do this? That's a tough problem. So instead of trying to just use some sort of second order logic solver to actually do that, we're going to use a technique called program synthesis in order to do it. And alternatively, you could also search, you could enumerate all possible expressions at that point, but that's also, doesn't seem like it's going to scale too well, right? Okay, so we're going to use a technique called program synthesis, and the underlying notion there is that given a limited set of ingredients for a fix, you can try to search for how those ingredients can be combined in order to create something that actually satisfies our constraints. So we've got a limited set of ingredients, and the question is, how do we combine them? And if we can't find a fix with one set of ingredients, maybe we'll, we've got a hot dog, but we don't have ketchup, maybe we'll add ketchup to it. We'll add another ingredient and see if that gave us what we wanted, which I guess would have been lunch. Bad time to have a class. Lunch is not the best time to have a class. Anyway, so if we solve this second order constraint, then we end up getting this fix at that statement. So f of all of these inputs, the program state at that point, is this. Upset plus 100.
Why isn't it 101?
Because this works.
That's what I was asking in the first place. It could be any number. It can give you a range of numbers. That will be more precise. And then let the user put a number over there based on the code.
It's naturally going to push toward the boundary conditions based on the semantics of the program, though, right?
Yeah, but it's not any more correct.
It depends on test input mode.
Well, the test input impacts the paths you follow and the concrete state that these variables have. Yes, it could be something else. You could get a different solution. This is true. You might not get this. You could get something entirely different. But if your correctness constraints are based over the path and you have some notion that tending toward the boundaries of these constraints is going to give you this, then that's what the solver will give you.
So what if it comes up with multiple solutions?
It could. You'll take the first. And this gets into this notion of coincidental solutions, where you have something that maybe it isn't really the right answer, but for the constraints you've got, it still satisfies them. And you could have multiple solutions. Some of them might be correct. None of them might be correct. And so you'll just take the first.
I feel like this is a really good way to solve the constraints and not fix the bug.
Potentially. We'll get to that sort of thing. And the notion of fix a bug is also kind of nebulous too, to some degree. Maybe work around the bug is enough.
Yeah.
I don't know. And that's still up in the air as far as this whole line of research goes, I think, when you look at automated repair. Because it's difficult to say you've got the right fix. In some cases, there's no such thing. In some cases, there's no such thing as a particular statement where the bug is. Sometimes you just have two different pieces of code and their specifications don't match up properly. Both of them are correct with respect to their specifications, but their specifications don't match. And as a result, you have this impedance mismatch that creates inconsistent behavior. So it's up in the air as to what this whole notion means when you're talking about fixing a bug in general. So we live with that.
Yeah.
Okay, so going back over everything, these are our steps again. We've got this ranking, we've got symbolic execution, we've got program synthesis, and you've seen Tarantula already. So we have these notions of evidence that are given based on statements executing inside the failing tests versus essentially all of the failing tests and passing tests versus all the passing tests. You should be familiar with this at this point, right?
Yeah, so I was thinking, instead here it says given a test suite, it works with Tarantula.
Mm-hmm.
Now to get that boundary condition, as you mentioned,
Mm-hmm.
is it not better like something like what Dart does or something where you generate a new test case based on that constraint which you are finding and then get the boundary test case?
This is interesting.
And then you feed it back and then you know exactly what boundary condition will satisfy.
There are a few issues with that. One, you're not entirely wrong. And if you look at applications for which concrete oracles exist, so for instance, if you look at web applications, and in particular web applications that generate new DOM elements, new elements inside an HTML page, you can say concretely, this is incorrect or not. We have validators that say this HTML is incorrect or this isn't meaningful or something along those lines. In those cases, yes, absolutely. In fact, there's some good work that came out of IBM which looks at test generation to drive fault localization. And so yes, in such a case, you could get more precise fault localization using a technique like that, absolutely. What about general purpose programs? Why is that hard for general purpose programs?
Don't have an oracle.
You don't have an oracle, right? So you could generate all those tests. Are they correct? I mean, you might be able to say this doesn't crash. So if you've got a crashing bug, again, crashing bugs are a little bit easier in general because of that sort of thing, then that's more helpful. But if you don't have a crash and your bug isn't a crashing bug, did you get the correct result? Somebody's got to go and evaluate that. And so it doesn't scale because you've got that human element that comes in. Now there's work on automated oracles as well, but it's only really starting to get off the ground at this point because that's tough. That's a very hard problem, as you would expect, I think, right? So because you can't determine whether or not the test passes or fails, adding every additional test is costly. But it is a good intuition. If you're in a domain where you do have that, then it's a good solution, with some caveats that we'll get to later, that apply in particular to the automated repair techniques, as opposed to the fault localization techniques. That will usually be good for fault localization if you have those oracles. Repair is more nuanced. Okay, and you're all comfortable with this then? Fault localization, good to go? Okay, so we've got our buggy program, we've got our test suite. It gives us a notion of ranking, and we can look at this ranking in order to figure out every repair candidate and just try them out. Okay, so symbolic execution. At this point, pretend this says var x equals a plus b minus c. I was going to make my own slides, but I didn't have time, so we have to live with the fact that export to PDF of someone else's slides didn't quite live up to the formatting there. Okay, so we have our concrete test inputs, and our entire execution is concrete up to the repair candidate. This is a little bit different again than we saw before. The entire execution is concrete up to that point, and then we make the result at that point symbolic. And we do our symbolic execution and look at the execution tree. There may be multiple paths that can yield the correct output then, right? So we have to take all of those into account. Some of the paths will yield incorrect results, but if we can produce correct results along some path, then we need to include the constraints for that path as a potential viable constraint that tells us what the correct behavior ought to be. Okay, so we're using this symbolic execution using only the result at the repair candidate as our symbolic variable, as our symbolic input. When we continue then from this function, we'll look at all these different paths and see what constraints they add. So for one particular input, we'll get one constraint. And notice that this is saying that for this particular input again, the constraint is tied to a particular input, because different inputs will give you different valid paths. So for this particular input, we end up getting this path constraint, and we get this outcome constraint. So you can see that along the false path, we have the output 0 equals 1, and so that's trivially false. So you can just prune it away. But over here, we have, along the correct path, we have x is greater than 110 and 1 equals 1, which is trivially true. But we have then essentially adding this constraint to our set of valid constraints. But we have a disjunction among all the possible paths from that point, right? Because they're all candidates for correct behavior. We don't know which path is correct. We only know which outcome is correct. So we have to use the disjunction over all those path conditions. Is that reasonable, or how? I'm just boring at this point. Okay, that's acceptable. Well, maybe not acceptable, but there's only so much coffee in the world. So then when we look at a repair constraint, the way we look at this is that over all the paths, for the path condition, the output should equal the expected output. And this is for a given test, right? So this is a repair constraint induced by a single test in our test suite. Over all the paths, we do the disjunction that the path condition, that we have the path condition that we observe, and that the output equals the expected output. Okay, this is just the generalization of that, right? It's the formula that provides that. I see a question, maybe?
I thought it was coming from the cross, but you just mentioned it's coming from the path that is correct. The constraint is coming from the path, the correct path.
Yes. Well, technically it's coming from all the paths, but the incorrect paths are going to be false anyway. They're not satisfiable because you know that the output isn't the correct output. Or the solver will derive that the output isn't the correct output. Okay, relatively clear? That's for one test. So then if we look at how this is affected by all of the tests, we have to take all of them into account, right? So we have the conjunction over all of the tests of the individual test repair constraints. Because you want every test to pass. So we're saying, well, this test has to be correct, and this test has to be correct, and this test has to be correct, and so on, right? That's why you have the conjunction there over the repair constraints for the individual tests, even though the individual tests have disjunction. Okay, that actually is relatively clear. Okay, excellent. How many people, out of curiosity, read the paper?
Just 2 pages.
Okay,
Beginning.
I think yes.
well done.
I read the paper before those funny symbols came into it.
Yeah.
Okay, so you didn't quite make it to all of the wonderful Greek and logic.
I read the paper and didn't read those.
We should go back through those then, because everything that I just described it's just what those symbols
Now
are.
it makes sense.
And understanding those symbols is actually important.
But I could just listen to you for 15 minutes. Or I could read those for 4 hours.
Oh, okay, so the challenge here, we've got time, we've got till 1:30 today. Okay,
Oh.
Yeah.
Well, I understand what you're talking about.
right, well, I mean, the challenge here is that in order to do this in general, you want to be able to interpret that kind of thing.
True. I figure you could work through it. I could work through it. Like, I could get through it if I needed to.
All these things.
Okay. I mean, that's the kind of thing that does make, term projects more challenging and so on as well. If people are interested in this kind of thing, because all these tools are available. You could go out and implement this yourself. All the tools used to make this are open source and available to you. But it's harder to do that if you don't struggle through the logic a little bit.
I do question why none of these tools are used.
Tarantula is used.
Yeah.
They claim on their website.
Does DCC include Tarantula? Is it based on the
It includes G-code. You can implement Tarantula in like 10 lines.
Why is it not a better prepared standard use thing?
This was published in 2013,
That's a long time ago.
Oh my God.
Okay. We have some different standards there. Anyway. So we have a notion of TS. Getting back on track here. TS is going to be the set of tests that we include in our repair constraint set. Now you might say, I want to include all of my tests in that set, right? Because I want to make sure all my tests are correct. That seems reasonable.
Yes.
Yeah.
But that will increase the complexity, and we only want failing tests because that will determine the constraint ultimately.
Almost. I think that's a good starting point, which is why it starts there. So we want to make sure we fix all the failing tests. This is true.
But you don't want to create a new constraint that will not work for the passing test.
Right. You don't want to break the passing tests also. So here's this conundrum we're facing. We want to fix the broken tests. We don't want to break the working ones. But if we add the constraints from all the working ones as well, we might get just grossly increasing complexity in our repair constraint. So what do?
We fix the broken one and then run it again with passing and see if it works.
Yeah,
And
absolutely.
Fix the failing ones again.
Absolutely. So we have this refinement-based approach where we start off by saying, well, we know we need to at least fix all the failing tests. So we'll do that. We'll start off and say that our tests for which we're going to derive these constraints will be all the failing tests. And we'll generate the repair. And so we've got this new program.
So you repair all the failing tests?
We repair the program based on constraints that will repair all the failing tests, right? Because we're guaranteed by our constraints that anything we add into our constraint set is going to be repaired.
Can we run into a problem where the program never ends because we keep fixing those tests and then unfix them?
You
for
only
different
have
tests?
so many tests. So you never take constraints out of this. You only add new constraints. So you have this monotonic growth. And you only have so many tests. So you can only add so many new constraints. And you're never going to stop satisfying the ones that are there. You might just say that this is unsatisfiable and there's no repair. At which point you move on to the next repair candidate. I see more questions.
Well, I was confused by that part. Say two of those tests we tried to fix it, and then because of that fix, the other two of those tests started failing, which were already passing. And then in the next cycle, when we tried to fix that, the other two started failing again.
Okay, so the issue is that anything that you've added constraints for can't start failing again, right? Because your fix is generated to satisfy those constraints, and the constraints guarantee correctness, right? What the constraints say is, if this is true, then this test will not fail. The constraint says, given these inputs, I will produce the correct output, right? That's why we collected those constraints.
So you don't change the constraints, you just change the piece of code.
You add new constraints.
Right, so we're adding new constraints. Let's actually walk through the example a little bit more because then I think it's going to be a little bit clearer. We start off by just collecting the failing tests, right? We all agree then you need to repair at least those, so you get the correctness constraints for the failing tests. This means that your repair will correct all of those.
Right.
It will make them behave correctly. It could make one of the previously working things fail.
Right.
But these would be previously working things that were not inside TS.
Right.
So in order to make sure you don't do that, you just run your tests again. This is because running the tests is cheaper than using all this constraint solving. So you just check those passing tests by running them again. And if none of them fail, then you know that you didn't need the constraints anyway. If one of them does fail, then you add in that test into your TS, and you add its correctness constraints as well. To enforce that, you will not make it fail. And so eventually, in the worst possible case, you end up adding all of your tests here, and you add the correctness constraints for everything, at which point, either you'll have something that corrects all of the tests at once, or you'll have a constraint that is unsatisfiable, in which case you know that you can't create a repair there. Is that okay? Okay, so we're all on solid ground.
So when you make some repair, and then some originally passing tests that fail, and then and then you add only those failing tests to TS again. That's it.
Exactly.
And then you remove the ones that were there.
You don't remove anything. You never remove anything. By never removing anything, what this guarantees is that your correctness will always increase.
So the previously failing tests are still there in the TS, and you add the
Yes.
newly failing tests.
Absolutely,
on top of that.
absolutely. If you threw things away, and this is why we see reunioning with the new failing tests. We're not taking anything out. If we took stuff out, we would not have this monotonic behavior, and we could become less correct.
In the worst case, you'll have all the test cases failing, and then you set a constraint that fixes all of them.
Yeah, absolutely.
What are we using to like solve the constraint?
In this case, they're using Microsoft's solver called Z3, or Z3 for those of you who prefer the more blasphemous alphabet.
It still like seems to me like it's very costly because you're adding new tests and it's like probable to, you know, corrupt the other one, add new, solve it again. It's like,
Yeah,
and
yeah.
it's only for one statement and we're going to like
Mhm.
do it with other
So it's
statements.
this trade-off that says that computer hours are cheaper than person hours.
Okay.
So the computer can go and do that work because it's a computer, and so that's okay. But it is potentially costly. It is potentially simple, and you do run a risk of not being able to generate a fix. That is all very true. And we'll get into more discussion of that once we look at the results that are in these slides, as well as the result. I'll try to bring up the results that are in the paper with the caveat that I can't see my screen. So I'll be trying to navigate things.
But that's the same case with the human also, you can't guarantee a fix with the human as well.
This is true. And in fact, it's often the case that you create an incorrect fix and commit that. This is a very common issue.
Because the human might cheat, but the computer will not.
Oh no, even if you don't have to assume that the human will cheat. People are fallible. They think they fix things and they don't. There's one bug that existed inside grep for a good decade. And every now and then, the authors of grep would go in and say, oh, we fixed this, great. And then they'd come back a little bit later and say, oh, this is a problem, let's fix that. Oh, we fixed this, great. They'd come back a little bit later and say, oh, this is still a problem. Oh, let's fix that. Oh, we fixed it, great. And it's, there's this almost this goldfish syndrome, right? Where you're just, or you know, cats and dogs running after shiny objects, right? Where you don't remember necessarily 2 years down the line that you already fixed this, and that your new fix is incomplete or incorrect in some capacity, because you can't see the full scope of the program at once. We just can't fit all of that in our heads. Oh.
Oh, just change the slide.
You have to change the slide.
Oh.
Mouse movement is.
They are really, really aggressive about that. Okay, so we have this notion of this failure-guided refinement to increasing our test suite. All right?
All the failing tests included right away.
Yes, yeah. Because you want to make sure you're at least correct based on the things that said you were incorrect.
You could just fix one test case and continually add tests.
Well, you know that in order to be correct, you at least want these though. So you might as well add all of them in the beginning. Because it doesn't do you any good to get something that's kind of correct and then say, well, that's not everything, so let's do a little bit more work. When you could just do all that work up front.
Depending where you're fixing one test case may fix everything.
Then the constraint should tell you that anyway. I can see your logic there, but hopefully, if that's the case, there will not be much subtlety in the constraints, and the underlying solver will be able to recognize that a little bit more easily anyway. I can see the justification there. I can see the justification.
Depends where the workload is.
Yeah, I suspect that you would be prematurely optimizing in such a way that in most cases that would degrade your performance. My suspicion. Okay, so we've looked at this symbolic execution now to build up these repair constraints. Now we have to get this last thing, this program synthesis business, which is funky. And again, I see brow furrowing.
Illustration is weird because.
Okay. It's good to know that the content is driving the deep internal discussion.
Wow.
So in the first case, if you cannot fix it, you go to the next rank.
So if you end up adding in all of your tests and
Still not fixed.
yeah, it's unsatisfiable, so you can't generate a repair.
Where do you have all the test cases? Nothing that says that.
You keep adding the newly failed tests. There's a limit. There are only so many tests, so the number of newly failed tests is strictly bounded by the size of your test suite.
That wouldn't be much because it takes a lot of time to run each test, right?
Depends on the program. Depends on the program. And this is something we should discuss when we get to the evaluation. We've got plenty of time. So.
Normally, like you have like, lots of loops, say. If it's a loop iteration and if there is
A lot of the
instruction
time,
inside
test
the-
suites are designed to be relatively fast to execute. Usually you want to have the simplest tests possible that meet your criteria, whatever your criteria may be. And so that helps this issue. It doesn't eliminate it. You're right that this is an issue. And as soon as we get to the evaluation, this should start firing some things in the back of your mind about how that question feeds into the evaluation artifacts and what all these things mean, and the realism and the applicability in different scenarios and so forth. So this is true. It doesn't necessarily invalidate the entire approach, which I think might be your thought. Does this invalidate things entirely? Things are a little more nuanced than that. Okay, so instead of trying to solve this constraint, this second order logic constraint for what is f, which is hard to do, right? The idea, give me this function. It's hard to make a solver that does that in a meaningful way. They're going to use an approach called synthesis. So the idea of synthesis is more that you have a notion of components that can be used. So we have, for instance, all of the input variables. These are some components in there. And we have ways in which they can be wired together, like plus and minus. So plus is a component, minus is a component. You might say that a constant value is a component that could be used. And there's increasing complexity among these components. So plus and minus are pretty simple. Multiply and divide are a little bit more complex. And there are things even more complex than that as well. Okay. So we have these scales of these components. But you can see that on the whole, if we say that we've got some ingredients, we've got our input variables, and maybe we can say, and I have one addition operation. Then I can ask myself, what are all the ways in which my input variables and an addition operation can be wired together in order to potentially produce the correct result?
How is multiplication more complex than addition, besides like the underlying logic?
The underlying logic. That is the issue.
So in digital logic design, we use Cardinal nodes to do something similar. If the
Okay.
complexity is not much, like till 3 or 4 variables, you can easily do it manually with manuals. And there are computer programs which does it for like a few more variables. But yeah, it does get complex with time.
Right. So the issue here is that you want something to be as naive as possible almost in terms of how you break these things down in order to make it scale. Because the issue is that you don't know what things meaningfully relate to each other and which things don't. I'm not sure exactly how Carnot maps fit into this conveniently.
In the end, it's just an AND or a AND gate. AND gate or a OR gate,
Sure,
which
sure.
which is being used for a number for different
But
variables.
in terms of like the semantics of,
Yeah.
well, what happens with plus and so forth, yes. This abstraction gives things,
And I guess there must be some machine learning techniques for this also. I'm not sure.
there may be. I think that's intrinsically difficult though. I mean, that's essentially the same thing as saying machine learning for SAT. I mean, for particular problem domains, that might make sense. I'm not sure, I mean, this is a particular problem domain. I'm not sure if it makes sense though. But so for instance, their table of complexity for these things, where is that? Is in table 3. So their first level of complexity is constants. After that, they have comparison operators. After that is logical operators. After that is arithmetic operators plus and minus. I guess this is all in the context of if you're changing a conditional statement even. And then after that, you have things like array accesses. Each one of these adds a level of complexity to the underlying reasoning. And so you'll only say add an ingredient from a lower complexity level to your recipe and then try it out. And then see if you can instead add in another ingredient from a higher complexity level. And it's just a question of, you've got these components, can you wire them together in some way that they produce, that they satisfy your constraints? And so what they do in order to do synthesis is create a set of constraints that represents the fact they've got these components and the fact that they can be wired together, and then throw that off to the solver.
They throw it off to the solver. What do you mean by that?
Well, they're creating a set of constraints that represent things like, I have these components, and they can be wired together. And so this gives you a notion of what the components are and what the parameters are. And it gives you a notion of, and essentially what they throw to the solver is, how are these wired together? Which we're going to look at on the next slide, but it's more the notion of, given the possible ways in which these things can be related to each other, can I find some satisfaction of this relationship that satisfies my repair constraints? So let's take a look at how this is applied. But ultimately, you're solving these two problems. Where are you placing these things, and what are their parameters? And this is really just, how is everything wired together? Given these ingredients, how are they wired together? So we derive this through a notion of a location variable. And you might notice that this code over here looks a lot like what you see inside LLVM. So we've got something that's basically almost a 3-address form, SSA form kind of thing going on here, which means the result of an operation can be represented by this logical variable. And this is essentially the location of the result for this operation. And this uses something that is a location representing a result of something else, or in this case, an input, right? Which is like we've seen with LLVM, right? Okay. And so the question then is, how can we solve for what locations are involved in this underlying program? So let's say I've got an addition. What are the locations involved with its parameters? What things does it use, right? Because an addition is one of my ingredients. I've told the system I'm giving you an addition to play with. So what are the things that it can have? And this tells you what the parameters would be. And that in turn also gives you this notion of, okay, then I'll just solve also for what the return value is over all of these things in my computation space. And the solver will just reason about how they are wired together. So maybe I had an R1.5 or R0.5, pardon me, in here, which was a different input. Okay, input 1 and input 2. Well, the solver can reason about, well, if I have R1 plus R0.5, then that gives me, that satisfies my input constraints. But R0 plus R0 does not, right? So figuring out how these things are wired together is what the solver does. Figures out how these location variables are connected. And that's the synthesis problem. Given a fixed number of ingredients, they can do that. And that's how synthesis is more feasible than just come up with a solution to the second order constraint out of the blue. What you're telling it is, we have a fixed number of ingredients, and all the solver has to do is figure out how they are wired together. Is that more confusing or less confusing?
How does it, like this obviously a different topic, but how does it do that?
Well, you're just driving a set of constraints, right? So what could the input to this be? Well, it could be essentially anything that precedes it inside this list of instructions.
Okay, so it's just a logic solve, I guess.
Yeah. now, did you feel disappointed by that? I mean, there's, it's just a question of, creating the logical constraints that reflect that relationship.
It doesn't, it's not scalable by any means.
That's true. That's true. But we're looking at fixes to a single statement.
Yes, which is, and so your input. I would do it a different way.
How would you do it?
I like genetic programming with that.
Okay, the caveat there is, if you don't already have the fix somewhere in your code, you're never going to find it.
You can generate code without any other code.
How?
You have the same constraints, you have the same, your.
Genetic programming doesn't involve the constraints though. Genetic programming just says, I've got this code somewhere. Because it has to do things at a broad scale, right? Genetic programming thrives on numbers. It's evolutionary.
What I would take is those inputs, the information you have given there,
Mhm.
and then recombine that into various different ways to use that as my.
What it sounds to me like you're suggesting is the exhaustive search, small scale exhaustive search, which they compare against at the end of the paper.
Yes. And
So-
it worked very well.
It worked okay.
Yeah, they're the more intelligent version worked better, which is understandable. I've never been a fan of logic solvers.
They have their place. They have their place. I mean, there are limitations that come into play. Your questions about scalability are valid.
Mhm.
But if we're looking at simple fixes, they should be able to find them with certain caveats and constraints that we'll talk about.
And they can, they're very strong in their domain.
Okay.
They work very well.
We'll talk about it. It's always more nuanced than that. It's always more nuanced.
Okay, if we give that set of constraints to a human, like this and this and this and this
Mhm.
for this equation, how much time does a human take to do that?
Ages. So, I mean, you're considering an exhaustive logical search, which one, we're error prone at. We're not good at that. Don't forget though that we're not just considering searching this space. We're considering searching over this space. And we also have to make sure that it satisfies the repair constraint, which is going to be more complex. Right? And that's where people are really bad. We might be able to methodologically enumerate all of the possibilities ourselves to a given depth bound, but we'll be a lot slower and we'll be error prone. And we'll still have no idea how they relate to the repair constraint because we're really bad at that part. But computers are good at it. Yeah, that's how I would frame it. And bear in mind also that you could have lots of inputs, lots of potential inputs at this point. And the question is, given all of your operations to a given bound for your ingredient list and all those possible inputs, what's the size of your search space? Well, still not trivial.
Yeah, so do they they do remove redundant ones, right? So even if you have say 1,000 input and 500 test cases or something, ultimately if you reduce all of them, and then the final set of constraints which you get, which a solver can solve, how do you produce that? I'm not sure. No idea.
What is your notion of difficult?
Like in terms of time,
We'll see. We'll see.
which a human takes.
I will say it will always be the human. There's no question about that. Now, a person might have intuition that leads them to the right answer faster. Might. This is possible. But using the same process, the mechanized form is going to be the human every time. Questions?
How many constraints would you normally be working on?
This is a good question to ask. This is a very good question to ask. This is a very good question to ask shortly.
I will ask it shortly.
Okay, there are several. I hope you've been keeping track.
especially. There was something else.
Yeah, there were a couple of something else's.
Doesn't matter.
Okay. Yeah, so we have this notion again that we're just figuring out how these things wire together. We throw that to the solver, it reasons about this and says, hey, these things are wired together in some way, and we can take these constraints and use them to derive the actual program, right? By saying that, oh, you know, the first input to the addition is 0, so this is here, so we know how those are all wired together. These location constraints just tell us how everything is wired together. Everybody is bored with that. Okay. Or not? Okay. So, how does this actually come into some utility? They evaluated this on benchmarks from the software infrastructure, something other repository, bug repository, SIR. Yes. Software infrastructure artifact repository, something like this. I don't know. Anyway, and also on core utils, which is at least real, right? The first one is not real, and we'll see the nature of those things. For their individual components, they use Tarantula, which again, you could use something like gcov and 10 lines of Python, not problem. Clee, which is a symbolic test generation tool, or a symbolic execution-based test generation tool, also open source, also actually used on systems level code. And they use Z3 and their additional kind of wrappers around Z3 for doing the synthesis. Z3 is Microsoft's solver, which also is available to you. So all these ingredients are available if any one of you wanted to go and actually implement this. Although figuring out the logic would be required.
Is their tool not available?
I don't know. I would guess not. Probably not. I would guess not. Yeah. I mean, you can check. If it's any consolation, Thursday's tool is available.
Okay.
Anyway, so what do these look like? So we have TCAS, which is 135 lines of code. I would argue it's got something more like 50 lines of code that actually do anything. But it's roughly 135 lines of code. Schedule, Schedule 2, replace. These are all from the Siemens Benchmark Suite. There are a couple of things missing there from the Siemens Benchmark Suite, maybe even conspicuously. So there is some incompleteness here, and it's not clear why this incompleteness exists. They do mention that because they're using Clee, Clee doesn't handle floating point, that they can't use benchmarks that involve floating point. So some of the other benchmarks in the suite include things like Toadinfo, which does floating point matrix calculation properties. So that, it makes sense that it would be excluded. Some of the others, though, are things like string tokenization, which not so floating point oriented there. So not exactly clear why those are left out. They also look at grep, again with these injected bugs. And then they looked at core utils. And there are some standard bug sets from core utils. Okay, and you can see also these are still relatively smaller. Still relatively on the small side. I'll also add that this program right here has absolutely no loops. It's a dead simple program, and it is essentially optimal for reasoning about with a solver. It's a very simple program. It's also the one that has the most versions. So bear that in mind when looking at the results. It means that all of the results are going to be biased by right, which is optimally addressable by any solution that uses a solver. Okay. So if we compare on the SIR benchmarks, looking at the total number of bugs, looking at things that could be repaired, looking at things that could be repaired by Semfix, things that could be repaired by GenProg. Okay, and this is actually not the total number of bugs because there were 90. It's the total number that were repaired across both versions, which is a little bit different, right? So if you're looking at the total number of bugs, this line is actually about twice as far up. That is what it is, right? It does give you an indication, though, that there are some bugs that are fixed by GenProg that are not fixed by SendFix, and there's certainly bugs that are fixed by SendFix that are not fixed by GenProg, right? So, yes. And you can see that as the number of tests increases, the total number of bugs that they fix decreases. Now, in addition, they note that using 50 tests, that SendFix was able to repair 48 of the bugs, and GenProg was able to repair 16. Okay, and that GenProg ran about 3 times longer than SendFix.
Yeah, GenProg, when 50 tests would run out of time.
Is it possible to scale 90 to 45? Does it say that
What do you mean?
it says SendFix repaired 48 out of 90? Doesn't add 48. SendFix doesn't show 48.
You are correct. Yeah, the graph doesn't quite make sense. Graph doesn't quite make sense.
It really doesn't make sense.
The overall relationship is actually correct.
Okay.
The scale seems to be off. That might be an artifact of the PDF translation. I don't know.
But that graph is not in the paper.
This is true. This graph is not in the paper. We'll look at some of the stuff in the paper as well. Okay. But there is an interesting thing going on here. First, I should say, everything inside the Siemens benchmark suite, everything inside SIR, has lots of tests. I mean thousands of tests.
Oh.
They only use 50. We see an interesting relationship, right? Where the more tests you have, the fewer things you're able to repair. This is one of the things that we wanted to come back to, right? So intuitively, fault localization improves with the strength of your test suite. Why does repair seem to be degraded?
Time bound for minutes. Could it be because of that?
It's not the time bound,
Constraint.
the constraints. Yeah, you're adding in more constraints. Your ability to satisfy the constraints is reduced. So they're
Your
generating.
ability to satisfy the constraints in the time allotted reduces.
This is true, but the time bound isn't the big player. The fact is that you're adding in constraints that can't be satisfied.
So it just gives up?
Well, hold on. Can't be satisfied by your solver. Because the search space that you're looking for where the bug
Sure.
is like here. So
Mhm.
there's your bug. And then your solver can generate programs.
Okay.
So, oh, I see. So it's making the search space smaller, but that might make it out of the bounds of what your generator can do.
So there are a few issues. One, you're adding in more constraints because of additional tests. This is true. The other issue is that if you have a small set of tests, then the constraints are more likely to be compatible. You're more likely to be able to generate something that repairs those tests. If you have more tests, your correctness criteria are stricter. And so there's a notion of, are you creating a complete fix for the program, or are you creating a fix for a set of tests?
Creating a fix for the set of tests if it doesn't pass the rest of the tests.
Yeah.
My question is, if we add more tests, the only problem I see is with the time that the solver needs to solve the constraint.
It may be the case, well, it is also the case that solutions that work for this set of tests will not satisfy the constraints of additional tests. So you might come up with a fix for something that satisfies 50 tests, you add in a new test with an additional constraint, and that additional constraint is no longer satisfied.
Okay, so, but I think it makes sense to do the fix with a particular set of tests and then test it again on another one and see how the results will be. But, they haven't done this in the evaluation. I guess.
Well, so we looked at this notion of the feedback-driven process, right? Which is, I think, what you're describing a little bit more.
Yeah, like
Right.
what we have like in similar to machine learning, we have a
Okay,
train
cool.
test and then test it.
Okay, you've got a training set and then an evaluation set.
Evaluation, yeah.
Yeah.
The K4?
It's called K4.
Okay.
We
Yeah.
have divided to
That's
K
all.
section and one.
Cross validation.
Cross-validation, there.
Anyways, so I think, using like few tests shouldn't be like that bad if we do the evaluation right. Correct.
The issue is that those new tests add in different constraints, so it isn't correct for them. It wouldn't cross-validate.
We won't know until like we have.
That's part of what this. That's part of what this does. That's part of what this says. Is that when you have the additional tests, you're not able to come up with solutions.
Okay, yeah.
In the suite, the SIR suite.
Yeah.
I assume it comes with repairs, bug fix.
All the bugs are injected, so you know what the buggy version is and you know what the correct version is.
Okay. So, did they compare about to see if they actually fixed the bug? Because you know what the correct version is. Did they match the correct version?
This is a good question.
Come up with the good questions, but no answers.
This is something that's been understudied in the context of repair, and we might have to get to a point where we turn the camera off soon.
Just any moment. Just tell me.
Okay, we can do that. Yeah, we should.
Just press.
Turn it off.
Okay.
Okay, so the lecture is finished.